Solutions and colligative equations, review sheet, more practice. I will work all the problems out that's on this extra review sheet, so please fast forward if you need to certain spots, but please try these questions on your own before you actually watch this video. Alright, question says, show all the work and complete the setup with the appropriate units. Use the solubility of solids to answer some of the questions. So number one says, write the dissociation equation for each. Now some of you are still struggling a little bit with dissociation equations. That's why I put this on here, and it's really something that you should have a pretty good grasp on. And again, it's just a matter of writing the balanced equation out first and then breaking it into individual ions. Individual ions is not the same thing as atoms when they're in their natural state, like gases. We don't have any gases in these ionic solutions. These are all dissolved and actually dissociated in water. A lot of you are still doing things like chlorine, bromine, iodine as I2. Those are not ions. Those are actually molecules. So make sure you know the difference between a molecule and an ion. Ions have charges. Ions have water molecules surrounding them. So A, sodium carbonate. Be sure that you actually write out the sodium. Carbonate, if it ends in ATE, that means that you have a polyatomic. CO3 with a -2 charge, so make sure that you actually have those charges. So sodium has a +1 charge. How do you know that? You look on your periodic table. Utilize your periodic table. It's going to really help you. So we want to make sure that the algebraic sum equals 0, something that we did earlier on in the year. So in this case here, we have Na2CO3. So 2 sodiums for every carbonate. When you dissociate this, we're going to dissociate these into ions. In other words, charged particles dissolved in water. So we never cover or carry subscripts that are not part of a polyatomic. Make sure you know your polyatomics. And make sure you can differentiate between regular atoms as well. So we have 2 sodium ions. So Na with a +1 charge, must show the charges. The charges indicate that we have this dissolved in water and it is an ion. You're not going to find a sodium ion just floating around in the atmosphere. You will find it floating around or moving around in a water solution. We also have 1 carbonate ion. So CO3 with a -2 charge. Now, if you were asked to involve this compound in either a freezing point elevation a boiling point elevation or freezing point depression, you would now have a multiplier or a Van Hoff factor of 3. You start with 1 molecule, it breaks apart into 3 ions. So that's one reason why you have to be able to write these things out, because you will be asked, and especially on these later questions, be able to determine the Van Hoff factor or the multiplier for those equations. So be sure you can dissociate these. Letter B, manganese 4 nitrate. Make sure you still know your Roman numerals. That's not something that we want to forget, especially when you're looking at the periodic table and it has more than 1 charge. We need to know what these charges or what these Roman numerals represent. So manganese, not magnesium. So Mn, and nitrate, again, NO3. So nitrate, -1 charge. Manganese in this case has a +4 charge. Don't go to your periodic table and decide what the charge is. The formula name is telling you what the charge is. So in that case, we have to use that charge. Since we have a +4 -1, that means we need to multiply the nitrate by 4. So in this case, this is what our formula looks like. Mn, parentheses, NO3, close parentheses, 4. We need 4 nitrates to balance that +4 charge for the manganese. This will dissociate into a manganese +4 ion, and then we're going to take that take this subscript here, 4, outside the parentheses, and indicate that we actually have 4 nitrate ions. So if you were asked to determine the Van Hoff factor or the multiplier, it would be 5. You have 4 of these plus 1 of those. 4 plus 1 is 5. Aluminum sulfate. Aluminum has a +3 charge. Again, looking at your periodic table to determine this. Sulfate, again, ends in ATE, so SO4, which has a -2 charge. So +3 -2, these are not balanced. So we need to multiply this by 3 and multiply this by 2. So that means we have 2 aluminums, parentheses, 3 for that. So when this breaks apart into ions, again, keep the poly together. We have 2 aluminum atoms, or ions, and we have 3 sulfate ions. If you were asked, what is a Van Hoff factor? You would say it's 2 + 3, 5. Very good. So don't always assume that the Van Hoff factor is always going to be 2, or it's always going to be 3, or it's always going to be 4. You have to write out the ionic formula and break it apart into its individual ions. All right. Question number 1. Not sure why it says number 1, but we have a second number 1 here. Awesome. Write the complete ionic equation and net ionic equation for the following. Show all charges for the ions. So here we have lead 2 nitrate reacts with lithium carbonate. My suggestion is be sure that you actually write out the formula first before you write out the ionic equation. So here we have lead 2 nitrate, so PbNO3. Keeping in mind, lead has a +2 charge, because it says so there. Nitrate's a -1. So that means that we're going to need 2 nitrate ions. Reacts with lithium carbonate. Lithium has a +1 charge. Carbonate, which we just wrote not too long ago, has a -2 charge. So that means that we need 2 lithium atoms. All of these reactions are double replacement. So I'm going to scoot these guys over. Okay. So double replacement reaction means that the metals are going to switch places. So the lead's going to go with the carbonate, the lithium is going to go with the nitrate. Always write the metal first. So lead carbonate, CO3, and let's move these charges over. Okay. Since lead has a +2 charge, carbonate a -2, that one's good. So we're not going to mess with that one. Lithium and nitrate, remember, just because it has a subscript here, that's not a polyatomic. Do not carry that subscript over. So it's lithium, Li. That's the way it appears on the periodic table. Nitrate, we will carry the subscript for the NO3, not the 2. So we go NO3. Okay. We know that nitrate has a -1 charge. We know lithium has a +1 charge, so it's +1 -1. That one is balanced as written. So now that we have our products charge-wise balanced, now we have to balance the number of atoms on both sides. So we have a +2 -2, +1 -1. I have 2 nitrates over here, 2 lithiums over here. That means that I need, actually let's scoot this guy over. A 2 right there. So now it's balanced. Then I go to my solubility sheet and take a look at that. And since I'm looking for, let's look at the lithium nitrate first. So nitrate here, is lithium any positive ion? Yes, it is. Soluble. Soluble means clear. No reaction is taking place with the lithium and the nitrate. Soluble means nothing's happening. Soluble means that the thing that we're in the water is dissolving, dissociating. It's breaking apart. It's not staying together. So let's take a look at the lead carbonate. So carbonate is down here. So again, these 3 have the same rules. So go across. Is lead an alkali ion? In other words, is it in group 1A? No, it is not. Is it ammonium? It is not. Is it any other positive ion? Yes, it is. Not soluble means we have a PPT, or a precipitate. So that is our precipitate. So what that means is the PbCO3 will stay together on the right side. We will not break that apart. So the first equation we need to write is the ionic equation. So we'll write the ionic equation as such. Pb +2 plus 2 nitrates. Showing the charges. So 1 lead, 2 nitrates. Notice how I have 2 nitrates, not parentheses 2. I have 2 lithium ions. I have 1 carbonate ion. Everything on the left side of the equation needs to be as ions. In other words, needs to have charges on them. I'll put a +1 there. On the right side, keep the PbCO3 together. The lead carbonate does not come apart. It is forming a new solid, so we're going to keep it together. However, the lithium nitrate is soluble, so we'll show it as ions. And you need to indicate how many you have of each. So we have 2 lithium ions here, 2 nitrate ions on the right side. How ironic. We also have 2 nitrate, 2 lithium on the left side. By definition, if these ions look the same on both sides, they are known as spectator ions. This is the ionic equation. The net ionic equation only shows the formation of our solid or for forming pure water. So we know that we're going to have lead carbonate being produced. What makes up lead carbonate? Lead ions and carbonate ions. Again, only show that which is involved in the reaction. No spectators ever show up in our net ionic equation. All right, so let's look at the next one. Take a look at that one. So part B says sodium hydroxide reacts with nickel 2 acetate, sodium hydroxide. So sodium hydroxide, again, write one of each, come back and check the charges. Sodium has a +1 charge, nitrate has a -1 charge. That one's good as written. We have nickel 2 acetate, nickel with a +2 charge. How do I know that? It says Roman numeral 2. Okay. Acetate, C2H3O2, and that has a -1 charge. So if I have a +2 -1, that means I need 2 of you. Okay? So there are my reactants. And let me scoot these guys over. All right, so now that we have our reactants, let's go ahead and switch partners. Sodium and nickel are going to switch places. So on the product side, we're going to have sodium with the acetate, C2H3O2. Sodium has a +1 charge. Acetate has a -1 charge. +1, -1, solid. Nickel and hydroxide. Nickel has a +2 charge. Hydroxide has a -1 charge. That means we need 2 hydroxides. So indicate it. Don't forget to put the parentheses around the hydroxide. I see too many of you just writing a 2 because there is no subscript. Anytime you need to represent more than one poly, put parentheses around it. Okay, so let's check and see how many of each we have. So we do not have the same number of atoms on both sides. I'm going to tell you that right now. So let's see here. I have 2 acetates here. I have 1 here. I'm going to put a 2 right there. So now I have 2 acetates on both sides. 2 sodium, I only have 1. I'm going to put a 2 there. Now I have 2 hydroxides, 1 nickel, 1 nickel. We're good. Okay? Next thing I want to do is check to see who forms a PPT. Sodium acetate, let's check that. So sodium acetate. Acetate is right here. Is sodium any positive ion? Yes, it is. That's not silver or mercury. It is soluble. The other one was nickel hydroxide. So let's find hydroxide right here. Is nickel an alkali ion? Nickel is not in group 1A. It is a transition metal. Go down to the next one. It is any other positive ion, not soluble, PPT. So this is our PPT. We're going to keep the nickel hydroxide together on the product side. So let's go ahead and write out our ionic equation. So again, we have 2 sodiums with a +1 charge, 2 hydroxides with a -1 charge, 1 nickel with a +2 charge, 2 acetate ions. Okay, so that's all the things on the left side. On the right side, our sodium acetate is not going to form a PPT, so it dissociates. So we have 2 sodium we have 2 acetates. And we have our PPT or our nickel hydroxide. So keep it together. Nickel hydroxide. NiOH2. Again, things that remain the same on both sides. Here is our arrow, just to help highlight that. So our sodiums are the same on both sides. Our acetates are the same on both sides. So writing the net ionic equation, and it doesn't matter if you say, okay, I'm going to flip this to put it in the same order. Whatever, that's fine. You got a plus sign there. However, if you want to write it like this, this too is okay. So I have 2 hydroxides plus 1 nickel makes nickel hydroxide. Remember, when you write a formula, make sure the metal's written first. Now some of you are probably like, oh, I don't want that over there. I want to put the nickel first. That's okay. That's great. Hey, that's awesome. So if you need to write the metal first, go ahead and do that. So if you want to move the hydroxide over here and then have your nickel ion right there, hey, not a problem. So tomato, tomato. So if you're like, no, I'm going to leave it the same way that it was written, you just go right ahead and do that. That's fine. Okay. So either way, whatever is on the left side, as long as it's respective for the arrow. But we can't move these guys around. Okay, we can't say, we can move these guys around from left to right, but we cannot flip these guys around. Okay, I think that makes sense. All right, the next one, number 2, says calculate the molality of a solution containing 74.7 grams of a molecular compound of methanol, which is CH3OH. I think we've seen that before. So a couple things here. First thing, calculate the molality. So again, molality is moles of your solute over kilograms of water. Moles of your solute. So our solute right now is the methanol. Our solvent will always be water. Super easy. All right. So what we need to do, we have a couple things. First of all, we have 3,400 milliliters of water. Now again, some of you can look at that and say, oh, I know how many kilograms that is. You will need to remember or memorize that 1 milliliter of water does weigh 1 gram, and that there are also 1,000 grams in 1 kilogram. So by doing that, you know that this is equal to 3.4 kilograms. That's probably pretty good. That'll save you some time. But some of you are like, oh, I can do that in my head, and you don't need to show that. And that's fine. Okay? That's perfectly cool. But if you do need to show it, make sure you do. So don't mess up in the regards of that there's 1,000 kilograms in 1 gram. That is not true. There is 1 gram in 1 milliliter. You don't need to go from milliliters to centimeters cubed. You can, but you're just doing more work. So this is not a required step that I need to see, but if you're struggling with being able to convert that into that, be sure you're showing it so you don't do something dumb. All right, we need to convert the 74.7 grams of methanol. So again, convert that from grams to moles. So let's see here. There's 1 carbon. So the molar mass of this is 32.042 grams, which means that we had 2.33. I'm going to go ahead and place this right here. 2.33 moles. Okay. So now I have my proper units, moles over kilograms. So let's find out what that molality is. 0.68. Let's say 686. That again is moles over kilograms. It's probably better to write it that way than little m. Okay. So I think it's pretty straightforward to calculate the molality. Take your mass of your compound, convert it into moles. Take your volume or mass of water, convert it into kilograms. And then plug it in, show that step, and solve. Number 3, what is the freezing point depression, the new freezing point, for a solution containing 423 grams of the ionic compound potassium phosphate dissolved in 4,000 grams of water? So freezing point depression, so we have a couple things here that we can maneuver. So we have delta T sub F, and again, the I and K sub F molality. So there's our equation that we're going to be using to work with. The first thing that we need to do really is to find out what our I value is, or what our multiplier is. So here we have the ionic compound potassium phosphate. So if it were molecular, your value would be 1. This is an ionic compound, so you need to find out what the I is. So potassium has a +1 charge. The phosphate has a -3 charge. That means I have +1, -3. I need 3 potassiums. Again, when dissociating this type of compound, do not carry that subscript because this is not part of a polyatomic. The phosphate is part of a polyatomic, but the potassium is not. So that means we have 3 potassiums with a +1 charge. We have a phosphate with a -3 charge. What I'm not showing is the coefficient there, but we start with 1 particle and we now produce 4. Dissociates into 4 particles. So my I value here, or my multiplier, is 4. Since we are freezing, the constant for the freezing is 1.86, and that's kilogram per mole. That value is on the back of your periodic table. It is in your notes. It is readily accessible. So please don't freak out or try to panic about where to find that. It's too easy for you. You just have to look for it. All right, now we need to find out what our molality is, or calculate our molality, or just insert the values for that. So we have, what do we have? We have 4,000 grams of water. There's 1,000 grams in a kilogram. So how many kilograms do you have? Very good, 4 kilograms. So we'll just put that right down there. And we have 423 grams of the potassium phosphate. So we need to do a calculation to find out how many moles we have. So 423 grams of K3PO4. Molar mass is 212.27 grams. 99. So now we can plug all that in, solve. I get a value of 3.7. We'll say 1. My calculator says 3.70651. So this is our freezing point change, or delta T sub F. So therefore, to do your final step here, it's going to change by 3.71. So we start at 0, and we're going to depress or lower the temperature by 3.71 degrees. So that means that the new freezing point for this water solution is -3.71. All right, here we go. Actually, let's scoot that up a little bit. Number 4, calculate the mass of a solute required to make 2.33 ml solution of a molecular compound C5H10Br2 in 1536 milliliters of water. Again, if you know the molality and you know something about the water, start with the water. We're not trying to use this value of water to calculate the molality. We know the molality. So make sure that you're reading the question. Make sure you know what the question is asking. This isn't a delta T equation. This is just regular old dimensional analysis. So start with your water amount, whether it's a mass or milliliters, because again, the 2.33 ml simply means that we have 2.33 moles for every kilogram of water that we have. So we need to know how many kilograms of water we actually have. So start with your 1536 milliliters of water. convert the milliliters into grams, convert the grams into kilograms, take your 2.33 molal solution, and if we were to, the question asked for how many moles, we'd be done. It wants to know what is the mass. One more step. Convert the moles into grams. So we have to actually find out what the molar mass for this guy is. Okay, so I'm actually just going to type that in right now. This molar mass is 229.93 grams for every mole. So I'm going to put 229.93 grams. How did I get that? 5 carbons times 12.01, 10 hydrogens, 10 times 1.008, 2 bromines, 2 times 79.9. Where did I get those numbers? The periodic table. So right now, if I were to stop here, my moles would cancel, my kilograms would cancel, my grams would cancel, my milliliters would cancel. I have grams of my solute. So we get to plug that in. 823 would be your answer. Grams of solute. So we would need 823 grams of the C5H10Br2 to make a 2.33 molal solution in 1,536 milliliters of water. Isn't that cool? Number 5, calculate the temperature that the solution will boil for a solution containing 3,000 grams of a molecular compound, C24H36O8, in 2,780 milliliters of water. Okay, a couple things you need to pick up on. Boil, molecular compound. 2 biggies to pick up on. So your equation, actually let's scoot that up a little. Your equation is delta T sub B. Your Van Hoff factor is an easy one on this one. K sub B, molality. Your Van Hoff factor for this problem, since it says it's molecular, is 1. Just because there's a lot of atoms in there, this molecular compound will not dissociate. It is a molecular compound. It is not an ionic compound. So your value is 1 for that. It is a big molecule, but this big molecule will not influence the deviation from the boiling point or freezing point as much as an ionic compound. So unfortunately, this big molecule will have a lower impact on that overall change. However, since it is still boiling, we use that constant, 0.51 moles. Now we need to find out how many moles and how many kilograms by calculating for the molality. And notice how I'm not actually finding the value for the molality, just as a necessary step. Finding the moles and the kilograms is enough. If you need to actually calculate the molality and then insert that value in there, just be very careful that you don't round too much and keep your units intact. Don't just put a little m here, actually leave it as moles over kilograms when working that out. All right, so our 2,780 milliliters, convert that into kilograms. Very good, 2.78 kilograms. And then we need to determine how many moles of this we have. So we have, let's see, 3,000 grams of our molecular compound. Notice 3,000 grams of the molecular compound, not of water. So make sure you can differentiate between those two. So we have, let's see here, 3,000. And 1 mole of that, we have, ooh, it's going to be a big number, 20. This whole thing has a molar mass of 452. And that's a big molecule, to be honest. Grams equates to 6.63 moles. So let's plug that value in up top. So we'll take that, stick it right up there. Okay. And let's find out what our change in temperature is. Our delta T, 1.22. That's our change in temperature. So, to answer this question, calculate the temperature at which the solution will boil. So we need to add that to 100. So actually, get that guy out of the way. So add that to 100 degrees, which is our boiling point. So your answer is 101.22 degrees Celsius. Okay. Not too bad, not too bad. All right, number 6. Calculate the temperature that the solution will freeze for a solution containing 95.3 grams of a molecular compound, C5H7OH, dissolved in 520 grams of water. Very simple problem, just like the last one. I hate to say it, admit it. Since it's molecular, pretty much the same thing's going to happen. I'm going to fast forward through this. So try it, and then let's see what happens. 1, because it's molecular. .13 moles. Put it up here. 4.05 degrees Celsius is the change for the freezing point. Water freezes at 0. Therefore, we will subtract by that much. So negative 4.05 degrees Celsius is our final answer. Number 7, calculate the volume of water needed to make a solution containing 352 grams of an ionic compound, magnesium nitrate, that freezes at negative 5.78 degrees Celsius. What a great question. So here's what we have. Haven't seen a problem like this, have you? We have a couple things, very easy. Just again, it's a little bit of a problem-solving question for you. Just checking to see if you're still good at things. We're looking for the volume, okay? Now, technically speaking, we don't have a volume in the equation, but we do have a kilograms, which you can work backward and find that volume. So that's what's happening. In this problem, you have a freezing point. So you have your delta T sub F, and you have I, your Kf, and your molality. Better written for your molality is this, where you have moles over kilograms of your water. What we're actually looking for is the kilograms of the water. That is what we're looking for right there. That's the value that we're looking for. So we know our delta T sub F, bam, right there. Since we know that water freezes at 0 and it had a change of 5.78, positive, because again, remember, whatever your delta F is, we subtract that from 0. So we know our delta T sub F is actually a positive 5.78. We know that. We know our I because, well, we will here in a second. Magnesium nitrate, we can find that. We know our constant. We can find out how many moles we have because we have 352 grams of the ionic compound. So we know this, and the moles. The only thing we don't know is kilograms. Let's work it out. First of all, let's go ahead and find out how many moles we actually have of the magnesium nitrate. Or, better yet, let's find out the Van Hoff factor, the I. So magnesium nitrate, magnesium, Mg, with a +2 charge. Nitrate, NO3, with a -1 charge. So that means that we have 2 of those. When it dissociates, we dissociate it into a magnesium ion and a nitrate ion. So our Van Hoff factor is 3. So we know that our I is equal to 3. We start with 1, we now make 3 ions. So we know that. We know our K sub F. Now let's find out our moles. So let's do that. So we have 352 grams. 352 grams of magnesium nitrate. Let's find out how many moles that is. So that gives us 2.37 moles. I'm going to leave that number in my calculator though. So now we know our delta T sub F, we know our I, we know our Kf, and we know our moles. So what we need to do is rearrange this equation to get a better equation. Let me see if I can scoot you down. Move you down, give you more room. I think this last one's good. So here we go. So we're going to rearrange this equation here to be where I actually take my kilograms, I'm going to multiply it on both sides. I'm going to divide my T sub F on both sides. So again, I'm multiplying kilograms on both sides, which will cancel it on the right side. I'm dividing my delta T sub F on both sides, so it'll cancel out on both sides. So now my equation looks like this. Kilograms is equal to the I, K sub F, moles over delta T sub F. Actually, that kind of looks sloppy. Let me rewrite that. Moles over delta T sub F. Okay, so that's how our equation looks now. Let's plug in the values that we know. So again, my Van Hoff factor, which we said up here was 3. Let's plug that in, 3. The K sub F, since this is freezing, get you out of here. The freezing is 1.86. That's degrees. I'm going to put the kilogram. Now, since we have more than one division line, I'm going to put that mole right down here, just to make it nice and pretty. So this is my constant. My mole value, I just calculated and found to be 2.37. So here, 2.37 moles. Again, I have the actual value in my calculator. And my change in temperature was 5.78, positive 5.78 degrees. Okay. As I always say, let your units talk to you. If you listen carefully, the units will tell you a story. They'll tell you if you're doing it right. If the unit that you're looking for, kilograms, is on the bottom, that's a bad thing. Okay? We don't want that. We don't want kilograms on the bottom. We want kilograms in the numerator. We want it on top. If you have the unit that you're solving for on the bottom, you have the inverse of the value. And I can't tell you how many times I see that. So, moles, gone. Degrees Celsius, gone. What's left? Kilograms, kilograms. Awesome. But we're not done yet. Let's get this value first here. So it gives me a value of 2.29 kilograms. What's the question asking? Let's make sure that we know what the question's asking for back here. Calculate the volume. So we're looking for the volume. Does it say what volume we need to be looking for? Could be in liters, could be in milliliters. Probably be better if we left it in milliliters, since that's what we've been working with. So now you just work backwards. Go, okay, I've got 1 kilogram. That means I have 1,000 grams. And then convert the grams to milliliters, and I would stop right there. So what we have is 2,290 milliliters. Cool. Isn't that a good question? Love that question. All right, we have another one very similar to this. Okay. Last one, number 8, says calculate the mass of a solution containing the molecular compound glucose, C6H12O6, which by chance has a molar mass of 180. I'm just going to tell you that. 180 grams. I know it's 100.1 something, but let's go with 1. Okay, so it has a molar mass of that. So I'm not going to waste a lot of time doing that. In 1,500 milliliters of water that boils, molecular, two really important things, boils at a temperature of 102.55 degrees Celsius. So the equation that we're going to be using, delta T sub B equals I K sub B molality. Okay? Write this better. Let's not put the little m there. Let's actually go moles per kilogram. Okay? Just to kind of clean things up a little bit there. Okay? So if it says calculate the mass, so what that means we're ultimately going to do is we're going to find out how many moles, then we'll convert to the mass. So let's see what we know here. Well, molecular means that the I is a value of 1. Very good. It doesn't dissociate. It's a non-metal or a molecular compound. So the Van Hoff factor is 1 because you have carbon, hydrogen, oxygen. There are no metals. The constant is a constant. The kilograms, we have 1,500 milliliters. We can find out how many kilograms that is. We won't do it just yet. The delta T sub B. Now this one, you got to be careful because it says the new temperature at which it boils at is 102.55. So if you're having a hard time figuring out what the change is, subtract that from 100 to get the change, which is 2.55 degrees. Okay, so the change is 2.55. Make sense? Good. Because if we were going and calculating the delta T sub B and we got that value, we would add it to the 100 to get 102.55. But to get this value here, the change in temperature, we need to take that value, the whole thing, the new boiling point, subtract it from 100 to get the change. Hopefully that makes sense. So we know this, we know I, we know K sub B, we know the kilograms. Hey, let's get busy. So let's rearrange first of all. So we're looking for the moles, which means that kilograms needs to be multiplied on both sides. And these guys need to be divided on both sides. So now the equation looks like this. Delta T sub B stays where it's at. It's not changing. We're also going to multiply that times the kilograms. Now, at first you're looking at that going, what's going on? Let your units talk to you. I'm telling you, if you let your units talk to you, it's going to keep you out of trouble. The I and the KB. Okay? Now again, don't freak out. Don't freak out and say, what's going on here? It's just another problem-solving question. That's all it is. Okay? Let's see if we can move these guys down a little bit more. Okay? All right, so here we go. So let's plug in some values here. So we know that our delta T sub B was what? 2.55. So let's get that going. So 2.55, and that's degrees Celsius. That's what delta T sub B stands for. The kilograms. We have 1,500 milliliters. Remember that there's 1,000 grams or 1,000 milliliters in a kilogram. So 1.5 kilograms. Okay. My I, easiest part. Molecular, 1. So my I value is 1. And there is no unit with the Van Hoff factor. It's simply a multiplier. So no unit goes with that value. So don't feel bad that you're not putting a unit on because there isn't one. The K sub B, that's our constant, which in this case is 0.51 degrees Celsius kilogram. Now let's not draw another division line here. Let's put that mole up here. Okay? So it's 0.51 degrees Celsius kilogram divided by mole. Put the mole on the opposite side. Okay? Let's see where we're at here. So units, degrees Celsius, goodbye. Kilograms, goodbye. What unit remains? Moles. That's what we're looking for. We need to find the moles, which I didn't write over here because we are looking for the moles. So whatever that value is, let's get a number there. 55 moles. And again, this is 7.55 moles of our glucose with a molar mass of 180.1. So let's just take 7.55, multiply that by 180. So 1 mole, 180.1. And again, that's the 6 carbons, 12 hydrogens, 6 oxygens. So that's very close. We'll leave it at that. So that times 180.1 is around 1,359.76. So we'll say that that's 1,360 grams. That is a good question. Oh, shucks, that's all. Okay, so again, trying to explain this. So we know everything but the number of moles. Once we know the number of moles, we can convert it into grams. Make sure that you rearrange the variables. Hope this video was helpful.